Section 1.5 is solution sets of linear systems. What we're going to find primarily in this section is that any system of equations or any linear system of equations will have a solution that can break down into two separate components. That's the ultimate thing that we're going to find in this section. First of those components is the homogeneous component, and then the other one we might call a particular solution or a specific solution or something like that. We don't actually name it, it's just another part of the solution. So to identify what homogeneous is, first let's define that. So a system of linear equations is said to be homogeneous if it can be written in the form AX equals 0. And the M subscript is just indicating that 0 is this is the 0 vector for the space Rm, m-dimensional real space, for the space of all vectors of m real numbers or tuples of m real numbers. So we'll probably drop that notation wherever it can be seen by context which dimension 0 vector we're talking about. And in this case, since A is an m by n matrix, we would be multiplying A by an n by 1 vector, and the result would be an m by 1 vector, which is this 0 vector here. So we don't need that subscript typically. We do use it one more time here, just to denote that this system always has a trivial solution, right? So if we have a matrix equation, AX equals the 0 vector, well, obviously, if we multiply the matrix A by the 0 vector, then we'll get the 0 vector in M space. So that was multiplying by the N space 0 vector, we'll get the M space 0 vector. So if you wrote out an example of maybe a 3 by 2 matrix or something like that, you'd see that this would be the 0 vector in 3 space. There would be 3 zeros in it, and this would be the 0 vector in 2 space. There would be 2 zeros in it. Nonetheless, we'll probably drop that notation for the rest of this section, as does the textbook. So the main question is whether or not AX equals 0 has a non-trivial solution. So the trivial solution is the obvious one, right? AX equals 0, well, we can just plug in X equals 0. We found a solution to this homogeneous equation right here. On the other hand, we might be able to plug in an X that's non-zero that makes this product 0. So that's the non-trivial solution that we'll seek. So it turns out, in not a very difficult manner, we can probably at least sketch the proof of this theorem below, but it turns out, according to this theorem, that the homogeneous equation AX equals 0 has a non-trivial solution if and only if the equation has at least one free variable. Remember, the language if and only if means that the first statement implies the second statement. So this statement implies this statement, and vice versa. That's the if part. Or the only if part, actually, so that the second statement implies the first statement. Now, this follows somewhat easily from the existence and uniqueness theorem of section 1.2. This is the second of those theorems, which states that a linear system is consistent if and only if, so we have another equivalence of statements, an echelon form of its augmented matrix has no row of the form given here, where we have all zeros and then a B in the right-handmost entry of this row, where that B is non-zero. Okay, so this is what we looked at before. This is a red flag for an inconsistent system, right? If we took the augmented matrix of a system, we got it into echelon form, and we found that we had a row of zeros leading up to a non-zero on the rightmost entry, we knew that this was inconsistent. These are 0 coefficients for every variable x1 through xn, yet when we multiply those coefficients, 0x1 plus 0x2 all the way up to 0xn, that's equal to some non-zero number b. Well, that's not feasible, that's not possible. So that's the inconsistent system scenario. Well, notice what we're dealing with in the present case. AX equals 0. Our right-hand side, all of our b's are already 0. So this is already 0 in the matrix, in the homogeneous system that we're considering. So there's no way for this matrix to be inconsistent. So that means that this matrix equation to be inconsistent. So AX equals 0 is consistent always, right? There's just no non-zeros in the rightmost column of its augmented matrix in echelon form because there can't be. Everything's a 0 over there. All the B's are zeros already. So we know it's consistent. And then the next way to see at least the sketch of the proof of this theorem is to realize that, remember the difference between a basic variable and a free variable. A free variable is one that doesn't get assigned to any value, right? It's a loose value. It doesn't have an entry in its, it doesn't have a pivot position in its column, right? So a basic variable is one that does have a pivot position in its column. Say something like x1 has a leading 1 underneath it in its reduced row echelon form, or some non-zero pivot position below it. Those are all the basic variables. Any variables without pivot positions or leading entries is the other term that's used. Something like a row of all zeros at the bottom of the matrix would indicate that there is a free variable in this system. So on the other hand, getting back to the point I'm trying to make is that if all the variables are basic, then X has to be 0 for all of them, right? They're all going to be assigned to something. So they're all going to be, they all have to be some certain value. Well, they're all going to have an entry in their matrix with a 0 on the other side. If you do back substitution on the very last variable, which is also basic, it has to be 0. So let me actually do this not in highlighter, do it a little bit more reasonably. We get down to the last variable, x sub n. Suppose that since every variable in this matrix, well, this coefficient here, I guess I should say, we get all the way through, we got all the way over to xn. Here's our right-hand side. And down here we have, perhaps this is a 1, right? We've gone to reduced row echelon form. Everything else ahead of it was a 0. And then right next to it here is a 0 in the right-hand side. Well, we know that xn must be equal to 0. And then if we follow that up, maybe to the xn minus 1 row, we realize that there's probably a leading 1 over here somewhere. 0 is ahead of that. And well, even if there wasn't a 0 here, we'd already know that xn, maybe this is a 2 or something like that, or in just echelon form. If this is the case, then we already know that xn is 0, so this is out anyway, and it forces xn minus 1 to be 0. And everything cascades up the line to make all the variables 0. So that would mean that if all variables are basic, then the only solution to ax equals 0 is x equals 0, the trivial solution. However, if there's one free variable, just using the converse of this logic, if there's, oh, sorry, not the converse, the contrapositive of this logic, if there's one free variable in this, then there's a non-trivial solution. So this is better understood in examples. Maybe you come back to this little sketch of a proof when you're done looking at some of these examples and working some of the problems, and it might make a little bit more sense. But for now, let's get started with finding homogeneous solutions to systems. And the very first thing we do is just start with a homogeneous system, right? So we have all zeros on the right-hand side. That's how we know we're dealing with a homogeneous system. That and the fact that there are no values on the left-hand side that are just numbers. Everything is a variable with its coefficient. There's no, 4 plus all of this, right? Without a variable next to it. That looks weird, and because it sort of is. Most of the time we have this thing over here on this side of the equation. So when all the variables are collected, we have all zeros on the right-hand side. That's how we know we're dealing with a homogeneous system. So solving this system, we're just going to reduce it to row echelon form, maybe reduced echelon form. So I'll write the augmented matrix down: 2, 1, -3, 0, reading off the first equation. 1, -1, 1, 0, 3, 0, -2, 0. So I see a 1 here. It's easiest to eliminate or to clean out a column with a 1 as your leading entry in that column. So I'm going to swap row 1 and 2. So using a little squiggle notation for that, it doesn't really matter what we choose there. 1, -1, 1, 0. We've got 2, 1, -3, 0, 3, 0, -2, 0. Might do the next step a little bit more quickly just to save time. Be sure to check it on your own, but let's zero out this 2 in the second row and this 3 in the third row all in one step with multiples of row 1 added to each of those rows. So row 2 is going to be itself minus 2 row 1. Row 3 will be itself minus 3 row 1. And what we end up with in this case is an unchanged row 1, 1, -1, 1, 0. And then we'll have zeroed out the 2. We'll have a 3, -5, 0. Below that, we'll have again a 0, then a 3, then a -5, 0. Okay, at this point, hopefully you've done enough practice to realize that whenever you have two rows that are identical in a matrix, in an augmented matrix, you can just simply delete one of those rows, right? Or sorry, not delete it, but convert it to all zeros, because effectively what you'll do is set R3 to be itself minus its identical row, which is row 2. And of course, that effectively zeroes the row out. You almost don't need notation for it. Of course, it just works. 0, 3, -5, 0. And this is echelon form, right? We don't have reduced echelon form, but this is sufficient to come up with a solution for this system. And well, maybe we take it a little further just to find the full solution set. But the first thing I can point out is this. Before we go much further, there's a non-trivial solution to this homogeneous equation. I know that because I'm looking at a row of zeros in my augmented matrix now. Even if I don't get to echelon form, which we could do a better job of by converting that 3 to a 1, but we're pretty close enough really, in terms of finding a solution. Even if I don't go all the way, I already know that there's going to be a non-trivial solution to this homogeneous system. I know that's the case because this row of zeros indicates that there's a free variable in here, right? In other words, only x1 and x2 have leading entries. x3 does not have a leading entry. x3 is a free variable. x3 can be whatever it wants to be, and we'll still have a solution to the system. So I'm going to take this one step further to reduce row echelon form. I'm going to do that by dividing this row 2 by 3. And I'll just simply write it down instead of all the notation. 1, -1, 1, 0. We'll have 0, 1, -5/3, 0, 0, 0, 0, 0. One more step to eliminate the -1 above this leading one. For reduced row echelon, just for the simplest version of solving this, we'll have 1, 0, 1 minus 5/3 is 3/3 minus 5/3 is -2/3. 0, 1, oh, there's a 0 at the end of that. 1, -5/3, 0, 0, 0. Okay, and the equations that we get out of this are the following. This implies the system x1 equals -2/3 x3, and x2 is equal to -5/3 x3. So there we are. So the last thing we can do is describe this solution set a little bit better. This is x3 is free, is the last comment to make right here. We'll often want to write this in vector form, right? And I'll give a full name for this form in just a moment. it looks a little bit confusing. We see that x3 is a free variable. It can be anything it wants to be. And as long as x1 and x2 follow these two rules right here, well, then we'll know that we have a solution to the homogeneous system. So we know we have a non-trivial one because we can pick x1 to be non-zero or x3 to be non-zero. So we let x3 be 1, and then we could check that what follows from x1 and x2 are still going to be solutions. So let's write down the vector form of this. The vector solution x is, as a column vector, it's -2/3 x3, -5/3 x3, and simply x3. Everything involves x3 in the solution. The last thing we can do is factor out x3, and this will be a common thing that we do in future problems: -2/3, -5/3, and 1. And then we just declare that x3 is some free variable. And that's the form of the solution that we'll tend to write this in. So we'll see why we do that in just a moment on the next page. Okay, so there's a single vector solution here with one free parameter or one free variable, x3. That can be any quantity we like it to be, just given the circumstances of that matrix. So let's take it just a bit further. Oh, and I think I just realized this. I made one error here with these signs. This is x1 minus 2/3 x3 equals 0. I jumped out a little bit too fast. It should be x1 minus 2/3 x3 equals 0. That means x1 equals 2/3 x3. So anybody who caught that sign error is correct to do so. So these are all positive values. It's just a small detail, but nonetheless, it's an important one. We want to get things correct. Now we should be able to check that that is in fact correct. The way we would check that is we could plug in any value that we want for x3. The easiest one we could imagine right now is just 1. Let x3 be 1, and that means we're going to check this vector as a solution to this system of equations. So you'd have 2/3 for x1, 5/3 for x2, and 1 for x3. You'll see that that satisfies all three of these equations. Okay, and then for that matter, you can let x3 be 100, and you could check that to solution or to the system of equations as well. So again, describe the solutions of the homogeneous system given right here. Okay, now this looks not like it's not much of a system, but a single equation does count as a set of equations. So this is technically a homogeneous system. For one, it's a system of equations because it is one equation. It's homogeneous because all our variables are on the left and the right-hand side is a 0. So that was easy to check. Now, there's not much work to do here, but if we write down its augmented matrix, it's going to look a little odd to us. 2, 1, -3, 0 is its augmented matrix. Maybe the one thing we do is put a leading 1 in the first row, 1/2 times row 1. We'll end up with 1, 1/2, -3/2, 0. And then maybe we stepped out from the augmented matrix to write x1 plus 1/2 x2. I'll take the care that I didn't in the previous problem to get this one correct on the first try. Minus 3/2 x3 equals 0. And it looks like, well, if we go back to the augmented matrix, keep this in mind. There was only one leading entry. There's only one leading 1. Right? This is technically, it's in reduced row echelon form. There aren't any other rows to have to fall into compliance with you. So not only are we in row echelon form, but we're in reduced row echelon form. So at this point, we realize that there are no leading entries for x2 or x3. So x2 and x3 are free variables. We're allowed to take values wherever whatever we like them to have. And then x1 is the only one with a constraint. And that constraint is given by this equation right here. This equation has to be satisfied regarding x1. So x1 has to be equal to, we solve for it, -1/2 x2 plus 3/2 x3. And again, x2 and x3 are free variables. So what does our solution look like? Well, we can write x as, remember, it'll be x1, x2, and x3. Well, x1 is -1/2 x2 plus 3/2 x3 we just found. Then x2 is just itself and x3 is just itself. Those are free variables. They just get written in as is. Well, remember matrix addition, or sorry, vector addition. I'm going to split up this sum as the sum of two vectors, and I'm going to keep the x2s together in a vector and the x3s together in a vector. And maybe for a clue as to how this splits apart, there's technically a +0 here, and there's technically a 0 plus here. This isn't absolutely critical. As long as you can see the decomposition gives us this given vector. When I'm done, that'll be just fine. So we can write it as -1/2 x2, x2, and 0, using the things on the left of the operators, plus the values on the left of the operators. And then we have 3/2 x3, 0, and x3. Those are the values on the right-hand side of the operators in the vector. So we split along those values. Again, the zeros over here weren't necessary, but I've written them in over here, and they are necessary here. We see that if we add these two vectors together, we'll get the vector that we've just decomposed. So this is accurate. Now we can furthermore factor out x2 and x3 from each of these vectors, like we did in the first example here, -1/2, 1, and 0 times x2 plus 3/2, 0, 1 times x3. So this is a vector parametrization of our solution. And this term is introduced on the next page. I'll mention that there in just a moment. One thing we might want to do here before I box it up completely is we want to kind of, maybe let the reader know that x2 and x3 are free variables. In other words, they're any real number at any given time. We can pick them to be whatever we'd like them to be. And x1 is the only thing that has to follow any rules and form our solution correctly. So if that's the case, what we could do is then pick x3 to be 0 and x2 to be 1. And that would mean that this vector, x1 being -1/2, x2 being 1, and x3 being 0, that's exactly what we were just saying anyway, right, about what these two values were. Plug that into this equation and see that it works. Similarly, let x2 be 0 and x3 be 1. This vector is gone. And we see that x2 is 0, x3 is 1, and then we've got x1 being 3/2, and we can plug all that in and see that we have 0 again. So these two objects, by the way, this is a single vector. The vector just points in one direction in three-dimensional space, right? If the only way we can generate different vectors related to it is by a multiple, some real number multiple or a scalar multiple of it, then we can only extend that vector along its length or contract it or point it in the opposite direction by multiplying by a negative value for x3. So this is really just the equation of a line in 3 dimensions. It's one way to think about it. Down here, we've got two variables. And just like I'd stated in a previous video, we have two vectors making up our solution. And we can add any amount of either one of those vectors by modulating x2 and x3. Well, if we have two vectors, imagine two pencils or two toothpicks or something stuck together at one end. It doesn't matter what angle you form between them or which way you orient them. They're always going to lie in a plane together. And those two toothpicks represent these two vectors. And that you can see how those two toothpicks would span a plane. So these two vectors span a plane in 3 dimensions, whereas this vector, x3 times it, spans a line in 3 dimensions. So all of these are parametric vector equations, and this is I've already introduced the term. Furthermore, that This is just a discussion of a plane being formed by the two vectors in the second example, and I went further to talk about the line in the first example. So we might be asked to describe a solution set in parametric vector form. That's using the parametric vector equation for a solution. So we'll see that in upcoming examples. So we'll end on a non-homogeneous system, and we'll be asked to describe all solutions AX equals B using parametric vector form. Okay, so this is as straightforward as other problems. The finish to it will be the only thing that's slightly different, but it'll be very similar to the examples we just did. We write our augmented equation, or augmented matrix rather, 2, 1, -3, 2, 1, -1, 1, 1, 3, 0, -2, 3. And I'll let the reader do their own work to go through the row operations to get here. I think it's a good exercise, but we've seen enough of these. I won't drag you through more of it, but we should arrive at an echelon form matrix that looks like this: 1, -1, 1, 1, 0, 3, -5, 0, and then a row of zeros below that. It's just a couple row operations away. 3 row operations to be exact away to get to here. The next step we could do is divide row 2 by 3, and that's going to lead us to a slightly cleaner version of this: 1, -1, 1, and 1. And we'll have 0, 1, -5/3, 0. And then lastly, let's go to reduced row echelon by cleaning out that errant 1 above a leading 1. And we're adding row 2 to row 1 to get 1, 0, -2/3, 1, 0, 1, -5/3, 0, and then that row of zeros. We're in reduced row echelon form. I feel that's the easiest way to pull out a solution, especially when we're going to have homogeneous and non-homogeneous solutions coming out of these things. So notice that this was not a homogeneous system because this B vector on the right-hand side was not 0. It's not the 0 vector. Okay, so, but it doesn't mean there won't be a homogeneous component to this. And we'll see that in just a moment, and you'll see what I mean by using that word too. So this augmented matrix in reduced form implies that x1 minus 2/3 x3 equals 1. x2 minus 5/3 x3 equals 0. And then lastly, x3 is free, right? There's no leading 1, there's no leading entry in x3's column. If we look down this, -2/3, -5/3 are not leading entries. They're not leading non-zero terms. And we get down to our last chance at getting a leading entry, and it's just a 0. So x3 is free. Now, we can solve for x1 and x2. x1 is equal to 1 plus 2/3 x3. x2 is equal to 5/3 x3, and x3 is free. And now we can construct our solution as a vector x. So x is equal to, it's x1, x2, and x3 as the entries. x1 is equal to 1 plus 2/3 x3. x2 is equal to 5/3 x3. And x3 is just x3. It's free, right? It's a parameter value in some sense. So x3 is a free variable. We'll be sure to write that comment when we're done. But let's split this up in terms of x3 values and non-x3 values. If we had another variable, we'd split along that variable as well. That'll look like this. We'll have 1, 0, 0 plus And then everything with x3, I'm going to write in its own vector, and I'm going to factor the x3 out of that vector and write it as follows. So what we typically do is we even drop the x3 multiple here in many cases, and we'll write it as 1, 0, 0, and then we'll use a different parameter, r, s, or t, or something like that. 2/3, 5/3, 1 times t, where t is any real number. T is an element of the real numbers, not specified. It can be picked by anyone. So our solution really looks like this. Okay, and there are two parts to this. Before, this is what a solution to the homogeneous equation looked like, and it's related to the fact that there's a free variable in the augmented matrix, x3, right? When there's a free variable, there's a non-trivial solution to the homogeneous system. That's ax equals 0. So this ax equals 0 solution is part of our overall solution to this non-homogeneous equation. And then we have the particular component solution. This is the 1, 0, 0 vector we have here. This 1, 0, 0 vector actually satisfies ax equals b. But notice that any solution in this form would satisfy ax equals b as well, because a times this vector, well, when it's times this one, a times that vector is 0, plus a times this vector is b. Well, then we get b out of that linear combination, or that combination of vectors that we have written right here. So I'll let the reader check that. You should confirm that a matrix A times the vector x equals b. Okay. And we should also check this furthermore. A times 2/3, 5/3, 1 t for any t value. So go ahead and plug in whatever t value you like. Maybe just try t equals 1 for now, but it will work for any one of them. Make sure that this is equal to 0, just as the other one was equal to b. So you should see that that checks out as well. So this, I think, suffices to sort of convince us this will always be the case. If we're dealing with an equation ax equals b, and we assume that it's consistent for some given vector b, and we're going to let p be a solution to it, well, then the solution set of ax equals b is going to be the set of all vectors of the form w, where w is a combination, it's a sum of p and v sub h. V sub h is the solution, any solution to the homogeneous system. So really, what does this mean? Do we have to go along and solve two systems each time? No, we don't. Look what we did for this one. We found the p vector here, and we found the homogeneous solution here, all just by pulling apart the reduced row echelon augmented matrix and rewriting that in parametric vector form. So those are the simple steps to this. This theorem just tells us that we're going to have solutions that decompose into these two parts in the most general cases. So one last thing to note is that the homogeneous solution to this, and note that this matrix A matches the matrix of example 1. We should note that the homogeneous solution here matches the homogeneous solution we found to that matrix in example 1, wherever that is, here, I believe. And this is exactly the case, right, for the same matrix. So, and that's exactly what we would have expected. So the homogeneous solution will just fall out of any general solution that we're looking for, and it'll be the components that involve the free variables. That's the most important takeaway of this section.